Hey, we're going to look at complex numbers. We know a complex number has an imaginary part to it. And we know that imaginary has I. You know, we've talked about real numbers a lot in math. Real numbers like your whole numbers and your counting numbers and your integers and your rational numbers and all those normal numbers that we deal with. Well, imaginary is kind of a little crazy, right? We can't really imagine it. It's not a number that we typically use when we're trying to count something or talk about money or really any typical real life scenario. Imaginary is just different, all right? So imaginary comes about when we try to take the square root of a negative. We know the square root of -1 is I. That is how we define the square root of -1. Because we know we can take the square root of a positive number, but when we try to take the square root of a negative, nothing times itself is going to give us a negative number. So we had to create this. So right here, coming from the book, it does kind of a decent explanation, but I want to try my own. So I is I to the first power. Let's just let it be I. When we're talking about simplifying I raised to a power, I raised to the first power is just I. You don't need to write the square root of -1. It's just I. Let's think about I squared. Well, this is the square root of -1 squared. And whenever we have a square root being squared, those cancel each other out and give us -1. I raised to the third power, notice we're counting up I to the first, I to the second, I to the third. I to the third power, well, this would be I squared times I. Breaking that down, two things we do understand. I squared is -1. So this is -1 times I. I cubed is -I. And if we go to I to the fourth power, this is I squared times I squared. -1 times -1 is a +1. So we can see right here, we've gotten a +1. If we go a step further, we've got the ability to use I to the fourth power. I to the fourth times I is I to the fifth. This is 1. I to the fourth is 1 times I gives us I. And let's add one more thing to this. If we go back to the beginning, let's look at I to the 0 power. Anything raised to the power of 0 is 1. So if we start to notice these outcomes, we've got 1, I, -1, -I, 1, I. We start to develop a pattern. 1, I, -1, -I, 1, I, -1, -I, 1, I, -1, I, 1. It's going to keep this pattern. It just keeps going. It's these 4 outcomes over and over again. I to the 0, I to the first, I to the second, and I to the third. And why I'm telling you all of this is because it's a very, well, first we might have to use this in other situations, but there's also a really common standardized test question that I want you to destroy if you ever see it. It's I raised to some power. I've seen it on the SAT, the ACT. I've seen it on placement tests for what math you're going to take in college. I've seen it on all these things. I raised to some power, we want to simplify it. We want to know this is equal to I to what power? And if we know this, if we know what I raised to each of these things are, simplifying these is easy. For example, let's look at I to the 78th power. I mean, this is just crazy. I mean, we could keep counting up. 1, 2, 3, 4, 5, 6, 7, 8. We can count all the way up to 78, and you can spend the next 30 minutes doing that, and then you still might feel like you did something wrong. Still seems a little sketchy. So, look at my method right here. We're going to take 78. We're going to divide 78 by 4. I'm dividing 78 by 4 because it's a cycle of 4 outcomes. We have these 4 outcomes over and over and over again. I'm dividing it by 4. And I'm going to go really old school, 4th grade division, and write remainder 2. The remainder is what we really care about. We don't really care about this 19. This 19 is just there. 19 is representing how many times we've gone through this cycle. We went through this cycle 19 times, and then we had a remainder of 2, which means I to the 78th power is the same thing as I squared. Because we went through the cycle 19 times and we landed with the remainder of 2. And so this is the same thing as I squared, which means this simplifies to -1. If I'm being asked what is I to the 78th power, it is -1. That is the simplification. Let's look at some more. I to the 53rd power, hey, well, we know we're going to take that 53, we're going to divide it by 4. 3 times. So this is remainder of 1. I to the 53rd power is the same thing as I to the 1st power, and I to the 1st power is just I. It's just I. That's it. Good to go. I to the -18th power, well, the first thing we need to remember is an exponent rule. Whenever we have a negative exponent, we're going to bring it to the bottom and make a fraction. This is the same thing as 1 over I to the 18th power. And now we can simplify I to the 18th power. We can take 18, we can divide it by 4. 4 goes into 18 4 times with a remainder of 2. So I to the 18th power is the same thing as I squared. And I squared is a -1, and 1 divided by a -1 is a -1. So I was talking earlier about real numbers and imaginary numbers, and we've got both. We've dealt with real numbers a lot, but imaginary numbers is what we're really dealing with right now. A complex number has both a real and an imaginary part. We can actually express any number as a complex number. For instance, if we want to talk about 4, 4 is a real number. But if we want to express it as a complex number, we would write it as 4 plus 0i. The real part is 4, and there's no imaginary values. Notice it's in the form a plus bi. There's a real and an imaginary part. If we wanted to think about an imaginary number like negative 16i, well, that is a pure imaginary number. There is only an imaginary part. But if we want to make it a complex number, we could say 0 minus 16i. So it has both a real part, there's nothing, and an imaginary part. And of course, we can have things like 9 plus 5i. This clearly has a real value, an imaginary value. If you hear the word pure, it means it only has imaginary or only has real, but a general complex number, we can express anything as a complex number, giving it a real and an imaginary part. Operations with complex numbers work just like you would do operations with a polynomial. I is treated as a variable. So right here we're adding these together, so we've got 3 plus I. That's it, we're done. We simplified it. Right here, subtraction, so I'm going to distribute that. 10 minus 2i minus 14 plus 6i. 10 minus 14 is negative 4. Negative 2i plus 6i is a positive 4i. That's it. That's simple, isn't it? Multiplication is going to work very similar. There's going to be a little trick at the end. So we're going to multiply this out. I know you know how to multiply. We got to distribute everything, or FOIL it, if you want to call it that. 14 minus 8i minus 21i plus 12i squared. Combine like terms. 14 minus 29i plus 12i squared. Notice there's an I squared. I squared is negative 1. You know that. You know it. So replace I squared with negative 1. And we have 14 minus 29i minus 12, which gives us a final answer of 2 minus 29i. Real part, then the imaginary part. We're writing it as a complex number. We're going to multiply just like before. 16 minus 20i plus 20i minus 25i squared. I distributed, multiplied it all the way out. Notice those middle terms, they are like terms, they cancel out, giving us 16 minus 25i squared. Yes, I squared is negative 1, so this is 16 plus 25, and 16 plus 25 is 41. See what happened on this last one? These two complex numbers, the only difference is the sign in between the real part and the imaginary part. From plus it went to minus. They are what we call conjugates. And because they are complex numbers, they're complex conjugates. Whenever you multiply a number by its conjugate, it does simplify down by the middle terms canceling out. In fact, here's a rule, really helpful. I'm going to refer to this the rest of the school year to simplify things. If you're ever multiplying a number, I'll use the I, actually. Let's just say A plus B times A minus B. If you're ever multiplying an expression times its conjugate, notice what happened here. A number times conjugate, middle stuff canceled out. It'll always turn out to be the first term squared minus the second term squared. Anything times its conjugate is going to give you the first term squared minus the second term squared. Notice what it gives us. It's a difference of squares. We are understanding our difference of squares. Something times its conjugate, it's going to be the first term squared minus the second term squared. Super helpful. If you understand that, it's going to save you so much time. All right, last example, we're talking about division. Okay, well first let's set this up so it looks a little more familiar. This is how we're going to see it most of the time. And the problem with this is that having an I in the denominator is considered unsimplified. That's the problem. An I in the denominator is unsimplified, just like having a square root in the denominator is unsimplified. So just like we would have to rationalize the denominator with a square root, we have to rationalize the denominator with an I. How are we going to get rid of that? We're going to multiply by the complex conjugate. It's the denominator that has the problem, so I'm going to multiply by the conjugate of the denominator. The numerator, we multiply across, we have 5 plus 10i minus 3i minus 6i squared. In the denominator, we're multiplying conjugates, so let's use our rule. It's going to be the first term squared minus the second term squared. Saved us some time. I'm going to simplify the numerator. This is 5 plus 7i minus 6i squared. In the denominator, I'm just going to leave this the way it is for a second. And we can change the I squareds to -1. So we have 5 plus 7i plus 6. On the bottom we have 1 plus 4, which gives us 11 plus 7i over 5. This looks pretty good, but we want to write our answer whenever we're dealing with complex numbers. We want our final answer to be a complex number that has a clear real part and a clear imaginary part. So right now it's kind of muddy. What is the real part? What is the imaginary part? Well, the real part is 11 over 5. The imaginary part is 7 over 5i. I'm making it clear this is a complex number, real plus imaginary. Hey, that's it. We crushed it.